Today we have a pleasure of hosting Shanghao Kong, a recently graduated PhD student from University of California, Riverside. And he's been working on few papers connecting information theory and diffusion models, something that our group is really interested in. And today he's going to present one of those papers and idea behind them. Yeah, please.
Yeah.
Take it away.
Yeah, thank you for your introduction. Yeah, it's my pleasure to give this talk about information plus diffusion theory. So today I'm going to talk about like maybe not only one paper, but just two or three papers like combination in the concepts, but they are very related and in the same domain. So yes, if you are good to go, I'm about to start. Yeah, okay. So can you see the slides or?
Oh, you need to switch in the swap displays so you can see.
Oh, okay. Okay. Watch. Okay, how about now?
Great. Yeah, great.
Okay, sounds good. So today my topic mainly focuses about information theory plus diffusion. So this is my academia work like with the Professor Greg Burstick. So next I will start from a very beginning. So this is diffusion model. Like before we know it's very well, we know that it just can generate an image, right, from a random noise. But actually, this process will be like the diffusion model will diffuse from a Gaussian noise step by step to a no noise image. So it's from time step t to time step 0. We call it the reverse of diffusion process. So a forward diffusion process is like from x0 to xt. It basically like add a Gaussian noise step by step, a little bit more and a little bit more. So we call it forward of the diffusion process, but what we call generate is about the reverse process of the diffusion model. It's like from xt to xt minus 1. But unfortunately, this process or this step is usually untrackable. It's really hard to estimate this p theta at xt minus 1 given xt. So, but most discussions of diffusion models just focus on sampling, right? We want to speed up their diffusion models or something like that. But we shift the focus to their role as a density estimator. So that's why, or what I think is more essential part of the diffusion model. It can like assumably to estimate the density of any distribution. So previously, this density estimation is usually be completed by this training loss, like BLB, variation lower bound. So when we talk about diffusion models, I want to talk about three challenges right in the diffusion estimation. Or maybe two. The first one is density estimation, right? How to estimate a very complex density. This is a challenge. And usually we use this oops, can you still see the slides? Sorry about it.
Oh no, the slide not.
You need to, yeah, yes.
Okay, it's good now. Okay. So previously we used this variation lower bound and we call it vanilla like diffusion. This is a suboptimal training objective, right? Because it's not exactly equal, it's a large or equal. So it's not an optimal training objective. A second challenge is like the interpretability of diffusion models. Although we know like diffusion model has very strong or solid mathematical foundations, but there's something very strange happens in our industry models. For example, like stable diffusion. I can give an example here, like use diffusion model to generate two images, right? The first one is a photo of a bat. No problem, you can generate something like a bat in the photo. A second image is like a photo of a bat and a ball. But something weird happened. The output image it only contain the ball inside, at least for our perception, right? So where is the bat? We don't know. And we draw some heat map or extract some features from their attention features, from attention layers. We can see the heat map of the word bat, but it just scattered all like in the whole image, right? So we don't know, maybe there is a bat ghost. So there must be something strange happened, but it's really hard to explain. We have to interpret that. So yeah, so after we talk about these two challenges, we can shift to our new domain like information-theoretic diffusion. It's kind of novel because this is a new bridge between the information theory and diffusion theory. So firstly, we can just regard the diffusion process as put a variable into a Gaussian noise channel. So here is an example. The X variable is the image of a dog. So we put some noise on it, and this level of noise is controlled by signal to noise ratio, like we named gamma here. So the Z gamma is like a variable with the Gaussian noise, but at different levels. So we need to like propose a concept here, like minimum mean square error. So it's basically like we want to denoise at every diffusion steps, right? So we get our estimate X, like X hat. We calculate the MSE between the X hat and the ground truth one. And at every different noise level gamma, we need to calculate this MSE. But there is a bound for that. We call it a minimum mean square error over or the gamma variable at a different signal to noise ratio. So for this optimization, we can derive an optimal denoiser, definitely like X hat star. Let's say endures the minimum mean square error, like MMSE. So actually here is already a relationship proposed by Gore, etc. They build up a bridge between the information and MMSE. So the relationship will be like, okay, the derivative of the mutual information equals to the half of MMSE at a certain noise level. But they don't propose is like how to calculate the pointwise IMMC relationships, right? So for example, when we calculate mutual information, we need to go over every data point in this data set maybe. But if we only give one data, like one data point, for example, give one image, can how to calculate or how to build up the relationship between this kind of information and MMSE. So that's why we propose this kind of pointwise IMMSE relationships. So you can see this equality just between the derivative of KO divergence and the pointwise MMSE. So you can see this MMSE is not go over the average data point, is just be at for a certain data point. And the relationship between the mission information and the KO divergence, they are very simple or trivial. So it's just from an interval or expectation to this kind of data point KO divergence. So we can.
I got a question.
Yeah, please.
So you have this MMSC, but now this is for specific point. But like for specific point, you're not looking at the minimum one because like minimum one would be 0, just predicting that point, right?
It still be a minimum one because previous minimum one we just to see two dimensions. One is data points, go through every data points, and another is go through every noise level, right? This is 2 dimensions, right? But now we just focus on single data point, but it will like minimum in at the all noise level.
Okay. So we're looking at the previous. Okay.
Yes, that's right.
So this is X would be a noisy image in this case. Then you're evaluating the KL divergence between posterior and prior, predicted posterior and prior.
Yeah, X is not X is a non-noise image, a non-noise data point. Yeah, but we could put it into a Gaussian noise channel, so we can just add different noise on it and do the denoise So after the whole process at different noise level, we can calculate this MMSE.
Okay, so this is pointwise in the sense of for a given noiseless image.
Mhm.
But you don't know that in advance. If you're on the generative process, you cannot do that.
I'm sorry, I can miss your question.
You cannot do that while running the dynamics, right? Because it's because you don't have the x will be like x0 will be the final destination.
Yes, that's right. So for example, how can we just calculate this MMSE, right? So we can just sample like for at a certain noise level, like gamma, we can sample multiple different noise, right? And add this kind of different noise onto the X and do the denoising. And then we calculate the MMSE to do the average. And we can just get this MMSE value. It's also like a pointwise. Yeah, did I answer your question or?
I'm still kind of confused because for the pointwise, I don't see clearly the difference. So the difference is that, I mean, you get the expectation over the join in the typical MMSE, but in the pointwise, you get the expectation of the conditional.
Yeah, for previous like a non-pointwise MMSE, you need to go through every data point in this set.
Oh, okay. Oh, for every
Yes.
data point in the data set.
Yes,
Oh,
that's right. That's also the way we calculate the mutual information, right?
Yeah, okay.
Yeah, we need to go through every data point. But now we don't need to go through every data point in this set, but just for one data point X. And also like only like for one data point X, we cannot calculate the mutual information, but we can calculate this KO divergence. Yeah. The expectation of this KO divergence equals to the mutual information.
And so you're saying that this is the mean square error per data point in the data set, right?
Right. Right.
So what consequences this has? Because I guess in the sense that we care for, I don't know, minimization to minimize over the whole data set, right? Or am I missing something?
Yeah, but not all. Sometimes you want us to meet.
Oh, okay. Because then it comes the relationship with the density, right? Because you want pointwise.
Yeah, that's right.
Oh,
That's right. Yeah. Okay. So
thank you.
Yeah, no problem. We need to clarify this question. Okay, yeah. So here, what we want to say is like we propose this kind of pointwise IMS relations, but currently we don't see what's a function of these relationships. But later we need to go through that. So the main takeaway here is just this pointwise IMS relations. So we start from very simple examples. For example, we have a block, like block A, and we just drop it, let it drop freely from position A to position B, right? We can see the change in this kind of gravitational potential energy. So the delta U, right? It's basically like the mgHb to minus mgHa. So this is an energy difference. So the similar thing for diffusion model, we want to convert the a cluster of a Gaussian noise to an image. So it's also the transition from Gaussian noise to image, from a density 1 to density B. So naturally, we want to define a free energy function. Is basically like this potential energy function. So we call it fx gamma. So you can see this is also a difference, but it's a difference from KO divergence for Gaussian and the KO divergence for data distribution. So we can visualize this kind of free energy function. What does it look like? So the KO divergence is between PZ gamma given X and PGZ gamma, or the PZ gamma. The PGZ gamma is just a Gaussian noise because we put it through a Gaussian noise channel. And PZ gamma is a data point, a clear data point, after adding some noise at gamma level, right? So we have this condition probability. If this condition probability close to like PG, means it close to Gaussian, this free energy function will decrease, the value will decrease. But reversely, if we push this conditioning probability to be closer to the PZ gamma, this free energy function's value will go up. So it's basically like the idea of this change in the gravitational potential energy, right? So we have this kind of thermodynamic integration just from the gamma zero, state gamma 0 to state gamma 1. So we also have two boundary case, right? When the gamma close to 0 and when gamma close to the infinity. So we just put this equation 1, equation 2 to this thermodynamic integral. So and do some simplification, we can get this negative local likelihood equation. But the problem is like, okay, we need to calculate on the right hand side, we need to calculate our integral, right? The integral inside of integral is a derivation of a free energy function, but unluckily, the second term in this free energy function is intractable because this PZ gamma is really hard to estimate, and we don't know how to estimate actually. We need to go over through every data point and go over through every different noise level. It's very computational huge. So if we still remember the takeaway on the previous slide, we can just we have built up this kind of pointwise IMMSE relationship. It's just a derivative of KO divergence and MMSE, right? So that's great. So we can just like replace or substitute this kind of derivative of free energy function to MMSE. So we just get rid of this kind of integral calculation, but do something like very calculable, like it's MMSE. MMSE is very easy. We just train a denoiser and do some denoising, like add noise, denoising, add noise, denoising at different noise level. So that will be very, very easier for this kind of an active local likelihood estimation. And
so just what is PG? PG is just a target distribution that you fix, or
oh no, PG is not. PG is just pure Gaussian, and PZ gamma is what we want to estimate because it's just a how to say, it's a pure noise at some noise at the gamma level. Yeah.
So, but the formula wouldn't be the formulas be fine for whatever choice of PG you put?
I'm sorry, could you just repeat the
Because
question?
the Gaussian is only defined at specific values of lambda, right? For a large, for small values of lambda.
Yes, that's right.
I'm sorry, of gamma.
I'm sorry.
Is it not working with the mic? Can you hear?
Yeah,
Can
I
you
can hear
hear us?
now. Yes, I can hear now. Can you repeat the question? So I want to make it
The
clear.
Gaussian is only defined for small values of gamma, right? Where there is no image anymore. But in this formula, you are using it for arbitrary values of gamma.
Yeah, that's right.
So where is it coming from?
Yes, and what I want to say, like gamma, it could be just like every noise level. So it could not be like just all like small bunch of it or small level range. Yeah. So did I like answer the question?
I just wonder where is PG coming from, because it's not the final distribution of the noise, because you are using it at every single time point.
Oh, that's right. This PG is Gaussian noise channel. So this is a prior, you can say, because when we put a variable into a Gaussian noise channel, we have a specific formula to calculate this distribution. So it's how to say, it's known. It's just a prior.
Mm-hmm.
So it is, I mean, to clarify, that is not the noise stationary distribution at the end of the diffusion, right? So it's not it is not the noisiest state of the diffusion at the end of the chain.
Yeah, it's basically not.
Okay.
Yeah, it just a PG just represent a Gaussian noise channel. Why we put variable into a Gaussian noise channel? Because this is very clear, like formula foundation. Because when we put a variable into a Gaussian noise channel, we can calculate this density, how to say, mathematically. Yeah.
So, my question was, you could put something else there. As far as it's tractable, the formula will still be fine.
Yeah. Yes, that's right. A Gaussian noise channel is not a only choice. You can put it into other noise channel, like a Poisson noise channel. That also be fine. Yeah.
Okay, thank you.
So yeah, where we go? Yeah. So now we just substitute this derivative for a free energy function with the MMSE value. So that would be easier to calculate, or it will be easier to train a model because we only need to train optimal denoiser, right? So clearly from this formula, so you can see this negative log likelihood will be a negative of a log of a likelihood of a Gaussian channel, and this is a prior because we can specifically calculate it out, and also integral over the difference of Gaussian's MMSE and data's MMSE. So to visualize it, there is a diagram. So the formula on right hand side could be regarded as the difference of two curves. The above one, the red one, is the Gaussian MMSE curves, like just put the variable go through a Gaussian channel. The blue curves is just like MMSE curves for the data distribution. So there must be a clear gap. And what we need to do or need to calculate is to calculate the area between these two curves to do an integral to calculate the area of this blue region. This green region. After that, after we calculate this integral, we can clearly calculate this negative log likelihood. And from the beginning to the end, everything, there's no like approximation. It's just equality, right, for this equation. And what we want to say or express here is like probability is equals to optimal denoising. So we need to like simplify it or to make it more specifically. So Rose prior, that we call prior, like you previous question, what is PG? So the PG can be right in another way. It's just a known distribution. So we can just calculate it or just write it out mathematically. So for Gaussian entropy and MMSE for Gaussian, they are just a constant. There's no variable inside. Like D is the dimension of the X, right? And the gamma is a noise level. So to simplify it, it could be like the negative log likelihood, just a integral over several MMSE terms plus a prior. And this prior is just a constant term. So after the derivation, it makes this estimation or density estimation very simple and it's easy to like execute. And we can compare our new negative log likelihood objective with the vanilla diffusion training objective, which is elbow or variation lower bound. So this variation lower bound just have three components, right? The first is L0 is a discrete reconstruction term, and L1 to T-1, they are MSE terms. They are also like use denoiser, train a denoiser to calculate that. And the last term is prior, like it's a prior noise. It should be whatever. It could be defined as Gaussian distribution, Gaussian noise. So similar thing compare with our training objective. The difference is like we are equity. So we has equality. So it's exactly the same. It's not a bound or approximation. But for the terms, yeah, We also have MSE terms, but for L0, we also incorporate it into MSE terms, so it's also a denoising process. So there's no problem. But for the prior, we also have a prior layer, just a Gaussian channel, so it can be calculated in advance. So they are also constant terms. So what's the difference? Like VOV is an approximation, it's not exact, but our IT bond is analytic solution, right? It's just exactly same. It's not an approximation. And the second advantage of our ID bond is like we only contains one integral over the MSE terms, and this MSE terms is easily to calculate, just to train a denoiser to do that. But for the vanilla diffusion bound, they also contain something like discrete reconstructed terms and also prior. And sometimes when we calculate those things, they will induce some errors. Okay, so we want to do some experiments to verify, like, okay.
Do you mind if I interrupt you for a moment? So isn't the formula essentially up to the constant term identical to the continuous sub?
Yeah, it's identical.
Okay. Yeah, so that's essentially you get, because the SNR in gamma space is just one, like, because usually you will have this SNR of t, dt, but that's absorbed in your parameterization, I guess.
What was the question for the
like
MTDT?
That in the standard formulation of the continuous algebra, you will have the integral of the MMSE times the SNR as a function of t dt, and I guess in your rotation that's absorbed already.
Yeah, like.
Yes. Yeah. The derivative just be replaced with MFC. Yeah. That would be easier for the calculation, right?
Yeah. Okay.
Yeah. So what we want to compare these two bonds, right? So we just run some experiments. So this experiment to calculate the negative log likelihood value. So we use a pre-trained IDDPM model, which is an improved DDPM, and we use our IT bond to fine-tune this model. So before fine-tuning, we use a variational. After fine-tuning, we use the variational row bound to calculate the NOL value for these two models. So for the original IDDPM models, they give negative 4.05 value, but after fine-tuning, they give a little bit higher value, like negative 3.85. But it doesn't make sense because we have fine-tuned the model. So naturally or straightforward, this value should be even smaller, right? But it gives a little bit higher value. So we want to propose a question: is this kind of variational bound estimates the NOL value correctly or not? So become worse after fine-tuning. So we use our IT bond to calculate the NOL value because we know we can calculate NOL value more accurate because its analytic solution is just exactly equal, but the VOB just give an approximation. So it's very hard to tell it's give an accurate number or not. So we use our IT bond to calculate these two NOL values for two models. Before the fine-tuning, it gives like negative 4.09. So it's very close to the original variation bound value. But after fine-tuning, we use our bound to quantify the negative log likelihood value. It gives a lower value. So that makes sense, right? So we can, from these experiments, we can conclude that the information-theoretic bound provides a more precise and faithful evaluation of a model density estimations capability. Okay, so let's almost or the essential part of the information-theoretic diffusion. So we can just summarize the three contributions here. The first one is we propose a new IMMC relationship and exactly diffusion bound. So this bond can train a model to estimate the density more accurate, or to evaluate a model is trained good well or not more accurately through our exact diffusion bond or IT bond. So the second thing is like the same optimization problem can also be exactly related to the discrete probability mass. So yeah, and this discrete probability mass, we can reduce the constant terms because it's very negligible. And the third one is like our approach allows us to fine-tune and ensemble existing diffusion models to achieve better NLLs. Fine-tuning, that's no problem. We have experiment for that. But how about ensemble? Like because for our formula, it's very easy. It's just the MLC difference between two curves, right? For here, because we put it through the Gaussian channel, so this right curve, it can be calculated in advance. But you can think about if we train a multiple denoiser, so we can get a multiple MMSE curves, right? Because sometimes, ideally, we get an optimal denoiser, so we can get one optimal curve for this blue one. But in reality, it's very hard to train an optimal denoiser. So the best way is like we train multiple denoiser. They give multiple different MMS curves, and we do ensemble to achieve the lowest ones, right? Or just for each region, there may be one denoiser achieve the lowest MMS curve. So at that region, we choose that optimal denoiser. So that could be ensemble or or we can call it a mixture of experts. So that would be easier to improve the diffusion models performance.
So,
and yeah.
So
yeah, please go ahead.
I tend to be quite skeptical about negative log likelihood for computer visions. And the reason is that essentially, usually you have this, especially in high resolution, you get very strong manifold structure in the image. And then essentially everything is divergent. Because then the log likelihood will be essentially a delta distribution. And if you try to estimate it with this formula, you will see that it will diverge. As far as you can fit the manifold, as far as you can fit the manifold arbitrarily well in even a small chunk, it will be already enough for making the likelihood diverge. As far as you get exactly on the manifold. And then I feel, okay, sometimes the likelihood is divergent, and then you are making it diverge a bit more, but you're not looking at the correct quantity. And that's why I'm a bit skeptical when people report the likelihoods, because okay, in some data, yes, it makes sense. But in some situation, I feel you could make it arbitrarily good in a completely trivial reason. So what is your take on this? Because I feel it's a bit it's a bit underestimated in the literature that this can be a serious issue that could really decrease the use of the likelihood as a metric,
Yes, that's right. That's a good point. Yeah, for the how to say, the image data point or the image data set is maybe not so ideal because it's kind of discrete data. But what we want to argue is we want to adjust the density estimation capability of the diffusion models is not only specific design for the computer vision data. That can be also to other continuous data, maybe for some other scientific domains, right?
Yeah, well, it's very useful. I wasn't arguing that it wasn't useful. Actually, there was a whole project that we started with a student, with Gianluigi, that failed because we didn't have that formula. And every time I meet someone, if I ask, oh, do you know how to estimate the likelihood? They say, oh, yeah, the trace estimator. I used to use the Hutchinson formula, and it's horrendously noisy. It's very expensive. Yeah. And so far, and I think this is incredible, since 2023, most people still don't know that the formula in diffusion for the likelihood can be computed kind of trivial in a super stable way. And I'm really trying to spread the word because this is super useful for scientific applications.
Yeah, that's right. Yeah. No worries. Thank you for this kind of concerns. But we also want to show there are several follow-ups from our works. The first one is extend to the discrete diffusion models, just a change, because we just build up our formula from a Gaussian channel, right? So if we change it to a Poisson noise channel, it can just convert this kind of diffusion models to a discrete diffusion models. And the second one is like we can use this formula to calculate or to estimate the mutual information between two variables, because here we got exactly equality between the negative log likelihood and the integral of MMSE. So if we later, I will just introduce the difference of two negative log likelihood will be the same as the mutual information. And the third one is like the third follow-up is like our from the information theoretic perspective, our diffusion model can be regarded as a noise classifier. That's an interesting new perspective of the diffusion model. So maybe let's get started with log likelihood ratio, like LLR. So I also give a very simple example, like we have two data points, like they belong to different classes, like the source P0x, they are class 0, and the target P1x is just a class 1. So if this PC equals to a half, then we use a Bayes rules to calculate to the log likelihood ratios. We can get an optimal classifier. So we can see this LLR formula, it equals to the log likelihood of the density ratio, right? Of the likelihood ratio. So if this LLR larger than 0, that means this data point X belongs to class 1. Otherwise, it means this data point belongs to class 0. It's very simple boundary classification. So if we don't regard the X as just one single data point, but we should regard it as a distribution. So we have a source distribution, also a target distribution. We can also train or regard this kind of LLR as a classifier for this more complex task, right? But in our diffusion scenario, there's a transition from a source distribution to a target distribution. For example, the source is Gaussian noise and the target is a distribution for image data, right? But we have multiple steps or 1,000 steps in the middle. So we just, at least log likelihood ratio would be like the P0 over PT, but we can use this kind of trick to have a chain of a log likelihood ratio, like P0 over P1 times P1 over T2, and so on. So for this each step, we can regard it, okay, the diffusion process actually train a classifier to identify which data point X, which class this data point X in the middle belongs to, right? Now, this is a new perspective to see the diffusion process. So then from this perspective, we can easily say, okay, we can build up two diffusion process. And one is like, okay, we got the noise data at the alpha level noise. So they are just corresponding to each other. So we can see it as a positive diffusion process. But we can also draw another level of noise like a beta, but it's not corresponding to the X alpha, right? The noise level is not consistent. But we can also, to calculate another diffusion process for that, we call it P zeta. So these two diffusion process, one is positive and P zeta is negative. So we can use this idea and combine with software plus function. It will be a conduct to a contrastive diffusion loss. So this contrastive diffusion loss will implicitly to draw a LLR classifier. It will just at each data point or each time step, it will just classify, okay, this data point belongs to our optimal denoiser or not optimal denoiser. So if we just push the model towards the optimal denoiser during the training, we can make sure the diffusion process or the diffusion model be trained well or be trained better. So we have a very simple example here with synthetic data, where the ground truth data and also the generative graph with our contrastive diffusion loss, and also the one with the standard diffusion loss. So we can clearly see that with contrastive diffusion loss, it will improve the diffusion model's discriminability, right? Because at each time step, it just implicitly train a LLR classifier. It will just push the model towards the optimal denoiser during training. This that is one.
Sorry, can you explain? I didn't understand how it works. Can you explain to me?
Yeah.
So okay, there are two models. One is the regular one, and the other is with the wrong noise. And then you are,
yeah, the zeta, like p zeta, is just with a noise data at up level, but give a wrong noise level beta. Yeah, that can be regarded as a negative sample.
Then you train with
or negative. Yeah, please go ahead.
Oh, okay, so that's the contrastive.
Yeah, that's a contrastive way, and you can see, although in this loss function, there is a subtract between these two log likelihood, right? So it's basically like a log likelihood ratio. It's basically like LLR. So it's just an implicitly optimal classifier here to identify which is an optimal denoiser, which is not. And it will push the diffusion model between towards the optimal classifier, optimal denoiser. Yeah.
What is why?
Sorry.
Or what is why? Like why in your equation?
Oh, why? Why is just an indicator? Yeah, you can just regard it as a class, like y equals to 1 or y equals to 0, corresponding to LLR like classifier.
Okay.
Yeah. Right. Yeah.
Other
Let's go ahead.
Oh
yeah.
Data. Why is there the negative b there?
Negative, you mean? Yeah. So this p zeta, the p zeta could be regarded as a negative density estimation or negative denoiser.
Okay.
Yes. So the next one is we're going to present in nearest workshop this year. So we use our information-theoretic bound to calculate or to estimate the image information. So previously we know that with our information-theoretic bound, we can calculate the NLL value analytically, and it's exactly equal, right? So, and also it's very simple to calculate this kind of conditional log likelihood. It's very easy because we only need to put this kind of this conditioning into the denoiser during the training, right? So after we calculate to estimate at least two, one is unconditional, one is conditional log likelihood, we can calculate this log likelihood ratio. And if we just draw our expectation on that, we can calculate the mutual information between X and Y easily. So that means we need to train two models. One is conditional, one is unconditional. So for training, I think that's very easy. We can just set a probability to drop off the conditioning. So yeah, so this is a training paradigm. Not much difference from the diffusion training, but just to have a probability to drop off the conditioning. So this is the experiment results. So we have more than 20 benchmarks set here. So we got a lot of different methods like mine, like Info-NCE, like NWJ and DOI. Also, the most strong benchmark is a Mandy. They have two versions or 4 versions. Our model called the MMG. So we test on those different benchmarks, and the broad truth mutual information is listed on the first row. We can see that there's some red part and the blue part. Red part means, okay, this estimation from the benchmark is a little bit lower than the ground truth. The darker the red is, the more far away from the ground truth. And also similar way in the blue one. The blue means the estimated value is a little bit higher than the ground truth. So in that case, you can see our model and our several variation. We can get the most like a best estimation out of these almost 20 tasks. And our best model can achieve almost or accurate estimation on this misinformation. So that's all benefits from the exact equality between the negative log likelihood and the denoising process. Yeah. All right. So let's talk about the information-theoretic diffusion. They're regarded as a bunch of implicit classifiers, and also use this exactly equality to calculate the misinformation. So the next, I will talk about interpretability, another big challenge in the diffusion models. So we do some adversarial attack. For example, we get an image data pair, image text data pair, like a turtle swimming in an aquarium. And we just put some postfix attack. So just put random characters after the prompt. Yeah, so actually those postfix attack, it doesn't make sense. It's just random characters, right? But it's actually changed the image from a turtle to a fish. But we don't know why. So we propose a question. Does stable diffusion really understand objects in the image from text, or there's some gap between the image distribution and text distribution? So a lot of people just have already noticed this question or problem. So they want to explain it from attention, because the fusion, like a different modalities fusion happens in coarse attention. So they want to analyze in that way to extract some features or probe some problems in the coarse attention. But it's very architecture dependent, right? And another is from clip score. It's clip score a very good metrics to evaluate the alignment between the text and image. But for that evaluation, we need a Prussian model. Yeah. Can we just calculate this alignment or explain or interpret this alignment just from the diffusion process itself? So we propose use information matrix to do that. So we draw some interesting experiments. Let's start from a very simple one. We give two images and give two labels for that. One's elephant, one's airplane. Similar thing, we put X and Y, the image text. Just only put the X goes through the Gaussian channels, and calculate this unconditional and conditional negative log likelihood, and calculate this log likelihood ratio easily to estimate this misinformation. So after that, we can calculate two kind of misinformation. One is image-wise, one is pixel-wise. The image-wise means for given image and given prompt, they output a specific value. That is the mutual information between those two variables. And another thing is we can calculate the mutual information for specific pixels to this Y, to the label. So that's a pixel-wise mutual information. So to visualize this pixel-wise mutual information, we can see, okay, it can clearly highlight the elephant pixels out in the elephant image, and also highlights the airplane pixels out in the airplane image. Yeah. So next, we want to do a more complex experiment. We give more information. Like we have a C, it contains the remaining words in the description of that image. For example, the background words, the old adult stands near where the wire fence, right? Or turbo prompt that is in the hangar for repair. So clearly, we can just calculate this kind of conditional matrix information. What does it mean? The conditional matrix information is like, okay, we want to evaluate the mutual information between X, Y, but subtract the information in C, like to remove the information in C when we evaluate X and Y. So ideally, because the C have some background information, it's just not so related to the information in Y. So ideally, when we calculate this conditional matrix information, it will give a more specific heat map, like it will highlight the more pixels of the elephant out instead of a background. So on the first example, with success, we highlight more pixels out of the elephant, right? But for the second one, we cannot see the airplane related pixels anymore. So that's just another question. What happened? So when we go back to check, well, let's see like the background or conditional prompt, we can see this background already contains a word like turboprop. Like turboprop have already on the information like airplane. So that's why we when we remove the information in C, we also remove this kind of airplane information out. So that's the reason why when we highlight the heat map, this mutual information heat map, we cannot find airplane anymore. So similarly, we do more experiments on that. But on the left-hand column, they are all non-words like elephant, horses, teddy bear, airplane. But on the right-hand side, we do some more challenge words like the verb, the runs, and the adjective, elderly, and adverbs like vertically, a number, etc. Something for on the right-hand side, there are some abstract words, right? For example, it's really hard to identify which pixels is corresponding to run and which pixels is corresponding to elderly. So let's see what does this model find out. So one particular interesting case is like elderly. So when we identify a person is elderly, is older or not, it's like we will see their facial expression. So you can see whatever the conditional and unconditional matrix information, they highlight the facial expression out of the people of this woman, right? That's very interesting. And compare with attention scores, right? For the non-words on the left-hand side, the attention score can do it very well. They can identify the elephant, they identify the horse, they identify the teddy bear. But for the abstract words on the right-hand side, there's no one except they all fails. They all fail. You can see there's a messy when we calculate this attention heat maps. So that's what we want to argue is that the mutual information or information matrix can identify those abstract concepts in the prompts, and corresponding that to the pixel space. So that means if we use the information matrix or information theoretic bound to train the diffusion model, it can improve this kind of multimodality alignment in diffusion models, right? And another thing is like for image generation, okay, there's no problem because everything is static. But if we want to generate a video, we give a prompt. In that prompt, every word just want to like make a difference, right? Especially those abstract words like the verbs, like the adjectives. It should like show some difference in the video generation. So if we can improve this kind of abstract alignment, abstract concept alignment in the diffusion model, it can definitely improve the video generation or video understanding. So especially for those abstract concepts like composition, like emotions. So to verify that, we just run another experiment. So we give an image and give two options to use the diffusion model to score which option is better. Here we use this conditional information metric. So for this example, if we calculate the CLIP score, the CLIP score is it gives higher score on the option 1, but clearly this option 1 it doesn't make sense, right? It cannot be the grass is eating a horse. But for our information, it can give a much higher, like is exactly double the score on option 2. So, which may indicate like our information matrix can give a really good understanding in this composition understanding task. But CLIP score like almost the same for these two options, or even higher for option 1. So it's definitely not a good or faithful evaluation matrix for this composition understanding problem. Also, we extend like to multiple categories, and not only this grass and horse like relation, but you can see other relations. We selected several out for this beneath and covered in for those two relations. The CLIP score is better than information, and similar category, it has 4 out of the 20 categories. But for the other 14 categories, the information metric is much better than CLIP score. Like for the holding, the sitting on, for those kind of relationships. Yeah, so from this experience, we can say the conditional matrix information is more faithful matrix for testing compositional relationships. And these kind of relationships are kind of abstract concepts into modalities, right? So also sum up 3 contributions here. The first one is like denoising diffusion model is easily interpreted by decomposing information. We can see that in the elephant and airplane examples. And another thing is more important is like mutual information or conditional mutual information are more faithful model agnostic matrix, because we didn't depend on the model architecture, not like the method extract some features from attention layers. And information matrix or the training objective is better to evaluate or better to train a model with a better, with a good multimodality alignment. Yeah. Then another thing is like information measures more abstract concepts like adjectives and adverbs, something like that. Also here, I also want to show some follow-ups here. Although those follow-ups are not from my group's work, but I want to highlight one of those. So this one is called Information-Theoretic Text-to-Image Alignment. They just derive this kind of information fine-tuning objective. You can see it's also the log likelihood integral, right? One's unconditional, one's conditional to calculate this kind of information. The only difference is like they derive a KIT, this kind of different schedule for this denoising process. So in this table 1, there are some alignment experiments. So you can see the information matrix fine-tuning, the MI fine-tuning, they are much better than the the reinforcement learning-based fine-tuning or post-training. So that means the information matrix has potential to improve the alignment of the textual image model, or maybe potential in multimodality models. And also some visualization. The first row is a color alignment, just to fine tune with other method compared with the stable diffusion to 2.1 base. You can see after fine tuning, MI fine tuning, it works very well. the color alignment, the shape alignment, texture alignment, and so on. Yeah, so overall from my presentation, we can draw some conclusions. One is like diffusion models can enhance density estimation when it combines with information theory. The second thing is like an information-based matrix can improve the interpretability and alignment for the diffusion models. And for the future directions, I want to explore. One is like how to make the model is more efficient. And that means efficient use of information, right, in the model. And the last one is a composable diffusion, which means like we have information from different objects, how to compose the different information together to generate a new variable, something like that. Yeah. Okay. Yeah. That's all about my presentation today. Thank you for listening. Yeah. If you have any questions, feel free to propose. Yeah.
Yeah, you may
Yeah.
Thank you very much for the nice talk. My first question is,
thank you.
In the slide where you mentioned about training, do you have like two parallel networks, or it's just like similar, just like conditional or unconditional? Because in the picture, it seemed like they have different parameters.
Different, which one do you mean?
Previous one.
This one?
Yeah, because
Okay.
So you have like two parameters, right? Or is it two different architectures, or is
actually they are just one architecture. For the training, for the formula, we just use the theta and phi to represent different parameters of model. But during the actual training, we don't do that way. We just drop out with the probability, right? For example, like 50% just trained without condition, and 50% trained with conditioning Y. Yeah. So this Y is optional. You see.
Okay.
So that's a standard quantum diffusion training.
Yeah.
Yes. Exactly. Yeah.
And so, how do you train? Like, or can you maybe give an insight why this leads to more efficient training? Or
for efficient, no, we didn't like optimize efficient for training here. But then one point I want to point out is like because here we just use synthetic data, right? So for the model architecture, we just designed by ourselves. Is a lightweight denoiser. It's just like it's not like the open source model like Stable Diffusion. That's too heavy for us. Yeah.
Okay.
Mm-hmm.
Thank you.
Yeah. Thank you for the question.
So can your formula also be used to find the likelihood for I guess, yes, if you want to find the likelihood at a given noise level instead of at 0, then you just integrate up to that noise level, or the formula needs to be modified substantially?
So integral for what? Could you just more like specify
so
the question?
So if you don't want to find the likelihood just of the noiseless image, if you want to find the likelihood of a noisy image at a given noise level.
Yeah, that's right. We just need to find likelihood of the noise image. Yeah.
But from the formula, you just do you just truncate the integral? Do you just integrate up to that noise level? How does it work? Because the formula uses the noiseless image through GAN, right?
You mean the formula uses the specific noise level for the image?
Yeah. Maybe can we go to the formula of the likelihood?
Previous formula or?
Yeah, just the formula for the likelihood, right? Yeah, this one. Yeah. Okay. So essentially, you just plug in for x.
This one or? Local likelihood ratio.
So if I'll just put the likelihood, like that was fine before. So if I want to estimate the likelihood at a given noise level instead of at 0, the essentially then x would be the noisy image. But then I need to retrain the network essentially, because or not. I guess I can do that analytically.
Yes. For training, we only actually this X is just clear image, and the gamma is a noise level or SNR level. And after we get these two variable, we just add specific level gamma level of noise onto this X variable to get a noise variable like Z. We have a so when we talk about Gaussian channel here, so this is the way like we calculate this noise variable Z gamma for different noise level, to put noise on the X.
It should be fine because like you're just having access to a score, which actually doesn't care where you're looking at.
Yeah, because it always points at zero.
Yeah.
You need to compensate, or you need to add something.
No, but it's just looking like score is looking at certain time points, so it doesn't know whether you're interested in whether you started at zero or not. Like it's just looking at like certain distribution at certain time point. So you can just use export to.
Yeah. Oh, here I want to mention like this gamma is not time step; it's a signal to noise ratio. It's a little bit different from the time step T. Yeah.
So why did you decide? Because this is a very strange parameterization for the literature. It's the first time I actually saw it.
This one?
Yeah.
Oh, that's from information theory, because then you get set like a.
Yeah, I get it. The formulas are very clean. You don't have any constants.
Yeah, we also like because the gamma means different time schedule, right? Or different noise schedule. So we in our paper's appendix, we also analyze the relationship between our schedule and also the schedule of DDPM, schedule of IDDPM, or cosine schedule,
So let's say if we're doing like continuous diffusion, and I'm interested in looking at the mutual information between, let's say, 2 pixels, given the rest.
There are the emission vision of 2 pixels.
Yeah, so if you have, let's say, 2 pixels into locations, and then I want to estimate what is their mutual information, can I do that straightforwardly with your formula?
Yeah, let me think about, I think it can do it. Yeah, it can just, you add noise on that specific pixels and do denoising to calculate the negative log likelihood of that specific pixels, and also do the same thing on another pixels. And to calculate, you get 2 different NL values, right? And to do the minus and get the log likelihood ratio, LR, and that will be the measurement of these 2 pixels. A little bit tricky is like when we calculate the measurement, there is an expectation, right? You see that? The expectation of this LR should be exactly the same as the measurement. So we should like go over like multiple these data pairs. Yeah. So for specific 1 pixels, you may even like it's a bit harder, I think, because we need to go over through every this kind of data pair. But I think if we just use this AOR to do approximation for that measurement, is also a feasible way, because for here those experiments we actually use this AOR as approximation to the measurement. Yeah.
I mean, at least we should be able to get decent approximations. So.
Let's try something, but I think the approximation that you get is actually some other information-theoretic quantity. If you approximate, I can show you.
Okay. We're trying to solve this problem. I think there are some interesting applications for.
That sounds good. Yeah.
Yeah, but I see that it's very difficult to convince Dayan to do anything approximate. So.
I see.
I still have a question
about. Sorry.
Oh yeah.
What's your question? Yeah.
Sorry. Yeah. Oh yeah. I still have a question on the computation of the likelihood, because so I get the point that you mentioned, that you kind of use this Gaussian prior as maybe as a reference, but typically, for example, I mean, in the case that you use like a variance exploring, so I don't know, like it will not be an isotropic Gaussian, but with a scale by some value of the stationary time. How how does that fit in your equation? Because typically you measure the change on the log likelihood, right? So you will always get the likelihood on the prior noise. That in your assumption you assume that is fixed, right? So imagine that my endpoint is maybe, I don't know, like in EDM parameterizations or the variance exploring case, sigma equals to 80. So you need to take into account that sigma, right? But in your equation, that doesn't come.
But I think that distribution is completely arbitrary.
So it's arbitrary?
As far as I understand, right? PG is a choice of reference. It's not forced to be the equilibrium distribution of the SDE.
Gotcha. Yeah, that's correct. Let's PG file.
Because that's what I'm confused, or how do you see it? No, because you typically for computing the likelihood you check. So basically the change, right? So how the evolution of the likelihood moves in the diffusion path. So you take the change, and that's why you get the likelihood at your clean state equals to the likelihood in the prior plus the integral, right? So, but here it seems like you don't take into account that initial prior. So that's where I'm a bit confused, or
because I think it's in the MEC.
Or it doesn't matter. So that's where I'm a bit confused. Do you get my question, or?
Yeah, so let me just want to understand your question. So it's really like what you mean? Why do we choose this PG as a prior, or?
So, or maybe to rephrase. So let's say that the typical setting, I don't know, in the variance exploring, you start with your data distribution and you want to map that to the noise distribution, which has some sigma value different than 1, right? Like 80. So instead of doing from 0 to 1, that will be a different Gaussian, right? So in the classical way where we estimate the likelihood, you need to take into account
trace estimation form.
Yeah, in the trace estimation.
OD flow.
Yeah, in the OD flow with the change of variable, then you get the log likelihood of the clean state equals to the log likelihood of the end state. Which if I get to choose a different end state, then that will have a different Gaussian with different sigma. But in your case, it seems that you fix that. So that's where I'm a bit confused.
Oh, okay. Yeah, that's a little bit different from last setting because this is a concept of Gaussian channel. So for a Gaussian channel, it's a prior setting. So we just fix it with a specific sigma and specific mean value. So we don't need to worry about that, about how to calculate this Gaussian entropy and the MMSE for Gaussian. They are just a constant through this denoising and add noise and denoising process. They don't shift or change.
So in some sense, the MMSE like absorbs.
Cancel out because you have two of them, right? It's a difference between two of them. So the concept they cancel out.
Yes, that's right.
Thank you. Yeah, I was so confused with that.
It's
no
simple
problem.
formula, but it's
okay.
Use this reference distribution.
Yeah. Great. Thanks. Other questions? I don't know. You think?
No.
Theoretical questions.
Do we have actually
Information theory questions.
So actually, have you ever looked at the neural entropy paper? Because I'm trying to kind of read that. Did you read the paper by Akil, neural entropy?
Neural entropy. Oh, I see, neural paper. Actually, they also incorporate the information theory into the diffusion process. Yeah, that's a very interesting paper. I don't remember there's an entropy matching rate. Is that method called?
Yeah, they try to match the entropy. That's what like.
Yeah, match the entropy rate.
Because the quantity that you are studying is essentially the quantity that we have been studying in our entropic time schedule.
Yeah, yeah. I just give a glance at that paper. I have not like delved into depths. So yeah, just from conceptually, yeah, conceptually they are very similar to our like ideas to combine the information theory into diffusion, especially for like entropy matching. Yeah.
Yeah, it's so that the kind of entropy is quite different, although it's probably connected because yes, this target distribution.
Target distribution, yeah.
Yeah, so that's an interesting similarity that you both are using a kind of a fixed target distribution for estimating. It is a kind of a bit different sort of entropy though that doesn't really connect to the likelihood of the data. So it connects to the likelihood of the model, not the likelihood of the data.
Not the likelihood of the data. Okay,
yeah.
I see.
So what you're doing is very similar to what also we have been doing with we're looking at this conditional entropy rate of x0 given xt, with essentially the same, right? Because you've been looking at mutual information, we have essentially the same formulas. We actually look at the probability of the model. So it's kind of the probability of the weights of the network, if you want to. So the likelihood, the information content that it's looking, it's about the model. It's not about the data points. It's a kind of an orthogonal way of computing the entropy.
Oh, I see.
It's actually worth reading.
Okay.
Yeah, exactly. I think the way it's written is really kind of for physicists, and it makes a lot of physics assumptions. So it's quite difficult to crack if you just come from pure information theory. Actually, I'm trying to work to write it down in kind of purely information theoretically, and I think.
Oh, I see.
Yeah, but it's interesting. It gives you if you properly understand what it's doing. Actually, we have this talk in the channel as well. So if you want to watch it, but if you properly understand what it's doing, it gives you a different perspective that you could be useful in some situations, I think.
I see. Yes, I have not get a chance to delve into depths, but I will watch your video, and I think that's a good good way to learn about that.
Yeah. Also, because there are a few people doing the information theory of diffusions. Oh, that's the other thing I wanted to ask, because I am starting to work with Giulio Francese from Eurocom, and he had some papers.
I mean, he's Minde, right?
Huh?
He's Minde.
I guess it's the Minde paper. So how does it differ? Because actually I didn't go in detail to his paper. How does it differ from your mutual information estimation?
Yeah, I also go through read several papers. Like actually, this Mandy paper is from their group. Yeah. Yeah, that's right.
So how is it related to your approach? Because the goal is the same, right?
I see. Yeah.
Now I wonder, do you know how it differs from your approach?
Oh, I see. I don't know about that.
Okay, you don't. You just did. We should really read each other papers, because there are few people that are doing this. And
we need to find more time.
We really need to start. I mean, me first. I knew about your paper way longer for a long bit of time, and then I read it when we're ready to derive out of the results. So
yeah. I see. Yeah, I think the information theory plus diffusion is not a very large group, so.
No, it's not. Yeah, exactly. So
so for those papers you mentioned, yeah.
We are like 6 people. No one in this other paper.
Hopefully next year. Yeah.
Sorry to ask that question, but I'm curious in the contrastive loss that you show. I mean, I find nice that you basically try to enforce kind of like the optimal posterior, right? So you kind of trying to make sure that you have the optimal posterior at each step. I was wondering, like, so in practice, do you use just the standard noise prediction formulation? So if you don't use any other fancy parameterizations like in the EDM paper, or you only use the epsilon as DDPM, right?
DDPM. So what's your specific question?
Oh yeah, my specific question is because I want to know if this works in the case that you don't need to, so you use the vanilla, let's say, epsilon prediction parameterization when you don't have any sort of preconditioning.
No, there's no conditioning. We use the vanilla DDPM models. Yeah.
And okay, and what is, so you insist that in this contrastive loss, you are enforcing kind of like to make sure that the optimal is warranted at each time. right?
Right, right. Yeah.
So I find that interesting because, so for example, in the EVM preconditioning, it's kind of like enforcing that, but so maybe this is.
Yes.
But
yes.
so you did not change anything in the noise sampler to make it more efficient.
No, we didn't make any change in sampler. Yeah, we just use this. Yeah.
So this is just like the linear is schedule, and that's it.
Yeah, that's right. Well, what's the aim here or goal here is like we use the CDU loss function to train a model, fine tune a model. Actually, we train from scratch to see if we can enhance the density estimation capability of the diffusion model. So yeah, that's the reason why we propose this CDO. And also, yes, conceptually, layer is something like Rose guidance, for example, the classifier-free guidance in some perspective. So we also want to derive like from information-theoretic perspective, how to interpret this classifier-free guidance. Yeah.
Okay, so if you don't have any other questions,
Let's move.
yeah, first slide.
No, I go back again.
I think we can thank our speaker for this wonderful presentation.
Thank you very much.
Thank you very much.
Thank you for listening. Yeah, thank you very much.
Thank you.
Yeah. All right. Yeah.
Bye bye.
See you. Have a good day.
Bye bye.
Bye.
Bye. Yeah.